Hello everyone, welcome to our first video of atmospheric physics. In today's video, we will be calculating the temperature of the Earth. Let's begin. So we all know that the sun shines its light on the Earth. Now, the light that the sun shines that is actually intercepted by the Earth is going to be captured in a cross-sectional area of pi r squared, where r is the radius of the Earth. And this is because that if we consider a larger area, say this area, then the outskirts is going to miss the Earth, right? So the actual area of light that hits the Earth is just going to be pi r squared, where r is the radius of the Earth. Now, since the sun is shining light on the Earth, and light carries energy, the sun is going to be giving power to the Earth. And the power per unit area that the sun shines on the Earth is going to be 1,370 watts per square meter. And that's called the solar constant. The solar constant. And the solar constant is, again, power divided by the area. Now, we know that light bounces off of objects, right? For example, if you had some sort of flashlight, let me just draw a flashlight real quick. And you just shine that flashlight on some object, like say a rock. Some of that light will just get bounced off the rock. Just pure scattering off the rock, right? The same thing applies to Earth. Some of the light that comes from the sun will get bounced off from the Earth. It's just scattering off the Earth. Nothing weird happening. Just bounces straight off the Earth. And it's going to go into space. So some of the incoming power, some of the incoming radiation will get bounced off, meaning that only a fraction of that radiation actually stays on the Earth. And the fraction, or the percent, of power that gets released into space is called the planetary, how do you spell planetary? Planetary albedo. And that's denoted as A. So this means that only 1 minus A, or really it's a fraction rather than percent, but 1 minus A of our actual power is going to stay on Earth. And since the power over area is the solar constant, that means that the power is the solar constant times the area that the Earth intercepts, right? So the total power is going to be Fs pi r squared. So 1 minus A, Fs pi r squared, is the power that actually stays on Earth. The next step is that we assume that the Earth behaves as a black body. Now, if you guys don't know what a black body is, I already made a video on Blackbody Radiation in my quantum mechanics playlist. So check that out if you guys aren't up to speed with Blackbody Radiation. But essentially, a black body is an object that will absorb light and it traps some of that light. And then it's going to emit that light afterwards. So blackbody radiation isn't as simple as scattering, as light scattering off an object. Rather, it's an object actually absorbing light and then emitting that light off as blackbody radiation. So the Earth is going to do just that. It's going to emit some light and absorb it, then release some of that light off. Now, black bodies obey what is called the Stefan-Boltzmann law. And the Stefan-Boltzmann law states that the power emitted via blackbody radiation per area is going to be equal to the Stefan-Boltzmann constant, denoted as sigma, times the quadrupled value of the temperature of the object. And this is where temperature actually comes in. So what's the power? Well, actually, never mind. So the area in this case is going to be the area of the Earth, since the Earth is going to be the black body that emits off blackbody radiation. So the area of the Earth, since Earth is a sphere, the area is going to be 4 pi r squared, I believe. So the power emitted via blackbody radiation, power via blackbody emitted, is going to be equal to 4 pi r squared sigma quadruple value of the temperature. So now what we have is that, like, let's just draw some tiny Earth. And the Earth is going to absorb, or not absorb, the Earth is going to take in 1 minus a fs pi r squared. And the Earth is going to release 4 pi r squared sigma t to the fourth as blackbody radiation. So now we are going to assume that the Earth is in thermal equilibrium. And thermal equilibrium just means that the power that goes in equals the power that goes out. So we're not going to have like any clouds or gases trapping in heat. The power that the Earth takes in is the power that goes out. Let's ignore these numbers, these random numbers. Let's just ignore them, these random numbers. So, since the power that goes in equals the power that goes out, and this means that 1 minus a fs pi r squared is going to be equal to 4 pi r squared sigma t to the fourth. We can then just solve for t to the fourth. That's just going to be 1 minus a fs pi r squared over 4 pi r squared sigma. This pi r squared is just going to cancel out. So t to the fourth is going to be 1 minus a fs over 4 sigma, meaning that t is the fourth root of 1 minus a fs times 4 over sigma. Let's just move these random numbers again. So if we were to actually plug in the value of the Boltzmann constant and the solar factor, which is, I believe, let's check. The solar factor is 1370, right? 1370 watts per square meter. And it turns out that the experimentally measured planetary albedo is 0.3, meaning that meaning that 30% of the Earth's light, 30% of the sun's power gets reflected into space. So A is going to be 0.3. So if you plug in Fs, A, and the Boltzmann constant, you actually get a value of that T is approximately equal to 255 Kelvin. And 255 Kelvin is equal to is actually equal to minus 0.67 degrees Fahrenheit. That's what I have written here. So that's pretty cool. So we have predicted that the average temperature of the Earth is minus 0.67 degrees Fahrenheit. That's about minus 1 degree Fahrenheit. If that was true, then we would be in an ice age right now. Well, we would be deep into an ice age. We are in an ice age right now, but we would be deep into an ice age, but we're not. So clearly something is, so clearly we aren't accounting for something. And the thing is that we did not account for greenhouse gases, because we assumed that clouds weren't absorbing any of that blackbody radiation that the Earth emits. If we take that into account, then our temperature will look more like what it actually looks like. Because it turns out that the actual average temperature of the Earth. So here's the predicted value. The actual temperature is actually approximately 288 Kelvin, which is equal to 58.73 degrees Fahrenheit. So that's the actual temperature of the Earth. So there's a big discrepancy here. And the discrepancy is caused by not accounting for greenhouse gases that actually trap in some of that heat. So if we didn't have any greenhouse gases, this implies that the Earth would be really super cold. And in our next video of atmospheric physics, we'll be making a model that accounts for these greenhouse gases. Thanks for watching. See you guys later.